Mission Atlantic, to ensure a sustainable future for the Atlantic Ocean. Integrated Ecosystem Assessment, or IEA, is a holistic approach to managing ecosystems by evaluating the cumulative impacts of natural variation and human activities. It follows an IEA loop that starts with scoping the system, together with stakeholders developing indicators, analysing the risks from and to different parts of the system, testing potential future scenarios under natural and anthropogenic change, and refine focuses on revising and improving the assessments based on the outcomes and insights gained from earlier stages in the cycle. This process helps balance trade-offs between ecological health, social well-being, and economic viability, ensuring sustainable use and conservation of ecosystem services. The initial phase is called scoping, which involves engaging with stakeholders to identify challenges to the system and to define objectives. This sets the foundation by outlining the study's scope, goals, and priorities to ensure relevance and targeted assessment. In this video, we are introduced to a method for creating, identifying, and harnessing relevant indicators. Our guides, Lucie and Benjamin, introduce a framework that extracts relevant signals from noisy time series. By breaking down the component processes of time series, this video provides a foundation for interpreting trend analyses, which are illustrated with real-world examples and explanations.
Hi, my name is Lucie Buttay and I work at the University of Tromsø in Tromsø, Norway.
Hi, my name is Benjamin Planque and I work at the Institute of Marine Research in Tromsø, and we are both involved in the Norwegian Sea case study in the Mission Atlantic project. In this video, we are going to introduce a method that is used in integrated ecosystem assessment. If you recall the IEA cycle from earlier videos, this consists in 5 main phases: scoping, indicators, risk analysis, scenario testing, and refining. Today, we are going to focus on indicators. What we mean by indicators are observation-based indices that tell us something about the state of the ecosystem. For example, when we measure sea temperature from a boat or from satellite, this can be used to derive an indicator of heat content in the ocean. Similarly, when we collect fish from scientific surveys or from fishing vessels, this can be used to derive an indicator of fish abundance in the ocean. Most of the indicators we have are summarized into one value every year. When put together, these constitute time series. Some of the time series we have date back to 100 years or more, and some others are much shorter.
One challenge for integrated ecosystem assessment is that we would like to compare and see all those time series. But often, those are presented in very different ways. Here, you can see a collection of time series. They have different temporal scale, and the vertical scaling can be very narrow or very wide. They can use points, lines, or bars. They can use color coding. They can use time series analysis, such as the trend showed in the lower right panel. All these differences make them very difficult to compare.
The method we are going to introduce is a way to analyze and visualize time series in a standardized manner. By using a common standard, this will help us to easily understand and interpret diverse time series from different parts of the ecosystem. The method is called ATTAC, which is the abbreviation for Analysis of Trends and Recent Changes. The output of the method is a collection of time series graphs for all the indicators reported in an integrated ecosystem assessment.
So what information do we want to get out of those standardized graphs? First, we want to know what the indicator is, its name, and in which unit it is presented. We would like to see the original data points. To help interpreting the time series, we also want to see if there is a long-term trend. And we want to see if there has been some extreme value in the past that could reflect anomalous years. We are also interested in what has happened in the recent past. Are we on the same trend as observed earlier, or are things changing and the trend is reversing? Are recent observations outside the range of what we would normally have expected? Here are 4 examples of the standardized time series graph, and we will explain how to read and interpret them. But before that, we need to briefly address theoretical aspects of what we call time series decomposition. Time series often exhibit complex patterns. To understand this pattern effectively, we decompose time series into 3 key components: the trend, the autoregressive process, and the noise. The trend represents the underlying long-term change in the data over time. It captures the overall direction, whether the series is increasing, decreasing, or remaining relatively stable over a long period of time. The autoregressive process reflects the short-term memory or inertia within the data. It reflects the fact that an observation in one year is related to an observation in the previous year. What remains is usually called noise. Noise represents the variation in the data that cannot be attributed to the trend or to the autoregressive process. Noise is unpredictable. It corresponds to the inherent uncertainty in the system.
So with this in mind, we can now go through one example of attack outputs. We start with a simple graph. The title is at the top, and that is the indicator for the biomass of blue whiting. The horizontal axis represents time. In this case, it goes from 1980 to 2025. The vertical axis represents the biomass, and the units are indicated as tons. On this graph, the vertical axis includes the zero, which is the minimum possible biomass that could be reached. Including zeros ensures that changes in biomass that are visualized on this graph properly reflect proportional variations. Without the zero, the visual representations would distort the relative changes, which can lead to misinterpretation. We have seen the title, time axis, and indicator axis. Now comes the observations. Each point shows the estimated biomass for a given year from 1981 to 2020. We can now decompose the time series of observations into trend, autoregressive process, and noise. The trend is shown as a yellow line that depicts the long-term variation over the period 1981-2020. When we add the autoregressive process, that is the memory in the system, we obtain the dotted line. You can see on this line that the value each year follows the trend and depends also on the value observed the year before. The third component of the time series is the noise, that is random variations that we cannot explain. We represent the noise in the form of a prediction interval, shown here as a shaded band. This is a 95% prediction band. It shows that for each year, if we did not have an observation, but only observations from the other years, we could predict that the indicator would fall within this band 95% of the time. There is a 1 in 20 chance that the indicator could fall outside. In this analysis so far, we have included data up until 2020. We have not yet included the most recent data. This is because we would like to check if the most recent observations are in line with our expectations. To assess this, we produce forecasts for the recent years and then compare our actual observations with these forecasts. We can now see the forecast for the 3 most recent years and the associated forecast intervals. If the trend and autoregressive process continue as before, we would expect the observations in recent years to fall in the forecast intervals with a probability of 50, 75, or 95%. We can now compare the actual observations with the forecasts. We see that they fall within the forecast intervals, but there is a tendency to depart from expectations in the later years. In summary, we have identified that there is a long-term trend in the biomass of blue whiting. This trend is positive, but not very pronounced. We have also identified that the biomass of blue whiting in any given year highly depends on the biomass the year before. And in recent years, the biomass is within expectations, but it is increasing at a higher rate than we would have expected. The attack method can be applied to many kinds of data series that are often included in an integrated ecosystem assessment. Here we show 3 additional examples: the North Atlantic Oscillation Index, the weight of mackerel at age 6 years, and the market value of the catch of thais. We can see that there is almost no trend in the North Atlantic Oscillation Index because the yellow line is almost flat. We can also see that there is no memory in this series from one year to the next because the dashed line is superimposed on the trend. And we can see that observations in recent years fall within the range of expected values. The trend in the weight of mackerel shows a decline from 2000 to 2010, followed by an increase from 2010 to 2020. There is no additional memory in the system from one year to the next because the dashed line is superimposed on the trend. If the trend had continued in recent years, we would have expected higher weight of mackerel, but we see that the observed weights are not increasing. Rather, they are close to the ones observed in previous decades. This suggests that the increasing trend has stopped. Data on the catch value of sace are only available since 1994. There is a clear increasing trend since then. We also see that the catch value in 1 year depends on the catch value in the previous year, as shown by the dashed line. In recent years, the catch value has increased as expected, with the exception of the year 2022, that appears to be an extremely high value. This observation, which lies outside the 99% forecast interval, calls for further examination by experts to determine what is the reason for such extreme value and what could be the implications. In this example, we have applied the method called ATTAC to analyze and describe the trend and recent changes in multiple time series that are used in integrated ecosystem assessment. The aim of ATTAC is to perform time series analysis in a transparent and responsible manner and to provide standardized graphical outputs. These outputs need to be complemented by expertise to explain the drivers and consequences of the observed changes. ATTAC, combined with relevant expertise, provides managers and end users an accessible way to be informed and alerted about long-term trends and recent changes in the ecosystem.
If you want to see more examples of the application of ATTAC, you can check the ICES report of the working group on the Norwegian Sea Integrated Ecosystem Assessments.
If you want to apply ATTAC to your own dataset, the computer code in the R language is freely available. You can access it from the ICES GitHub. And this code is part of the transparent assessment framework of ICES.
If you want to know more about this method, you can also contact us.
We hope you have enjoyed this video. Bye.